So today I was going to talk about a review of electronic converters for EV charging and then V2G connectivity. I think that's the topic Kaushik gave me, and then I said, okay, I'll do it. So let us see how this works. Okay. So just a few slides on where I am from, where I am located. So it's College Station, Texas. So it's very close to Houston, and we're close to the sea, right? And then if you go directly horizontally from Delhi, I'm opposite side. So it's just New Delhi, and then that one. So the weather is actually same as New Delhi, except that it's going to get colder because we don't have Himalayas there to protect us. So sometimes you can get freezing and things like that, but very, very rarely. Right now it's very hot. Right now it's like 40 degrees centigrade right now. And then Texas is actually suffering from a lot of energy issues right now because everybody's turned on their ACs, things like that. So we are a very large university. It's a land-grant university. So it's like 75,000 students. And then our engineering program has 25,000 students. When I went there, it was only like 5 or 6 majors. Now we have 21 majors. So all kinds of engineering, you can read there, material science engineering, manufacturing and mechanical engineering, and all things like that. So in the US, it's most, engineering is a undergraduate degree. So all undergraduate degrees are 4 years. If you take an accounting degree, biology degree, or math degree, or English degree, it's all 4 years. So, and then after that, you go to professional school. So medical is a professional school. So you can be an engineer and go to medical school, or you can be an English major and go to medical school, and then all kinds of things. Law is a professional degree, so you have to go to. After this, you go to law. A lot of engineers are now going to law school, right? So that's the brief introduction, and then I'm constantly learning different things. I'm working with a few colleagues for a couple of semesters. We launched a course called Automotive Electronics, right, with my electronics colleagues. So we do this class on, so I teach a part of this class on battery management, power management, but there are a lot of other things which the electronics professor teaches, and we have a very good, we have a Texas Instruments support on this one. And then as a part of that, we also have labs. We have developed some labs, and we're constantly improving it and things like that. If any of you want any information on this one, I can share it with you. Just send me an email. And so my presentation is basically introduction, and then single and three-phase EV chargers. And then more recently, we're working with a few companies like John Deere, not Chrysler, but John Deere on integrated EV chargers. This is just experimental phase. How can we do that? And then the fast charging. And then I said integrated solid-state transformer, because that's not yet commercial. That's what we're looking at. And there are other, if I have time, I'll look into other applications and skip over. And then a lot of V2X is happening because of ABB and others come up with bidirectional EV chargers about 11 kilowatt or so, very small. You can pick it up in your hand. So with those V2X grid services, frequency regulation of the grid, and if you have EVs parked in this building and EVs parked in the next building or across the street, they all can be electronic, they all can be pooled. And the pool can actually bid on the market and then do all of those things. Those markets are not here in India, but I think they'll happen soon. And then, so for the high frequency conversion, you need fast charging. So I'm a Tesla fan, so from Houston to LA, all those red dots are all fast charging networks, right? And so the EV plugs are so many. So this is what I have in my garage to charge it at home, and then when you go outside, you need any of these connectors. And so basically level 1, level 2, and level 3. So level 1 is usually at my home. And then, so we're going to review some level 1 chargers. Level 2 is basically also could be at home, or it's usually in a parking lot, or it could be in a hotel where I'm staying overnight, and I can get the EV charged overnight, slightly higher than level 1. And level 3, of course, is a fast charger where you go for, I said 50 to 100 kilowatt, but now it has become 350 kilowatt, right? So I was charging once and I got into 250 kilowatt. I was really scared to sit in the car. 250 kilowatts, I don't know, I don't want to sit here. and then it's very, very fast, right? Fast charges. So trends in, I think this is, you all know you're working in power electronics, you have different ways you're pulled out, weight, volume, losses, and then how can I keep on reducing these things, right? So I have today with me, I think IGBTs have become silicon carbide for all the EV applications, and then of course GaN. So line frequency transformers are still used, right? So they're all in the fast charging network, and so these are 60 hertz transformers with 11 kV or even 13.3 kV, I think, in India, in US, but here in US, India 11 kV, I think, 11 kV, and so the high frequency, switching is kind of important, right? So you have a 50 hertz transformer, 20 kilohertz transformer, and then high frequency basically reduces size, weight, and volume. And also switching losses are important, I think, for all the students. I think you're talking about soft switching and all of those things. I think I have a good slide here which says efficiency of this power electronic equipment, which is inside the box. So that efficiency is output by input. And then if I just look at output by input, input is basically output plus losses, right? So if I calculate the loss, I get this equation. And if I assume a 90% efficiency of this box, then I'll get 11 watts or so loss. Now, I have a designer B who employs GaN and silicon carbide, and he gets 99% or 98%, you can assume any of that. Then if he uses the same package, by improving the efficiency from 90 to 95 or 98 or 99, at least in this example is 99, you can go up to, with the same losses for the same package size, you can go to 1100 watts. That means you can pump 11 times more power. I think that's the reason why we are all working with efficiencies, and then although we are improving 95 to 96 to 97, I think previous speaker was showing the wireless charging, it was improving. There's a lot of alignment issues and things like that, and then trying to improve, you decrease the resistance and so on. So that's the importance of efficiency, right? And then the single phase grid connected EV chargers, I think the scooters don't, I think they are in the US, but not much used, right? So only in the campus commuting. But in India, I think all the other countries like Vietnam and China, before COVID days, I used to go a lot with China. So China has all these things electrified, bikes, and I cannot see a single pedaling bike. Everybody's going on EV bike, and then they're pedaling when there is an uphill and things like that. Including the guys who are carrying in the roads in India some motorbike along with a huge bunch of gas cylinders he's carrying. So all of those kind of buggies, and they all go in China in towns with EVs, but I don't see that much EV here. I think it's happening. It's going to happen soon. So you have a grid, AC to DC converter, then a battery pack, right? Texas Instruments has lot of resources there for you to design. I'm subliminally promoting Texas Instruments because they are in Texas, and then they support us so much. So single phase grid connected EV chargers, you have power factor correction, DC-DC converters, right? And then you have, of course, power factor correction. You need that here. And then these are mainly for EV scooters, right? So this entire unit could be residing on a wall, which you will see here, I think. Oh, I'm skipping something. Okay, yeah, this one. So this particular one, you can see that it is, it's on a wall. It's on a wall. It's producing 60 volts at the output DC, and then it has a 94% efficiency, this box, by Ether. And so those are available, and those have the structure. And then a grid-connected EV charger might look like this. I think Professor Ahmed, the first day, he presented some of these things, and then also he added some ZVS for these PFC stages, and then you have these zero voltage switching, trying to improve the efficiency of this stage, and then finally package everything, and then put it in a box. So I think as a students, when you're working on, you have to actually look into all the grid standards. What is the voltage sag? What is the, there's something called CBMA, or Computer Business Equipment Manufacturing Association. They produce the curve, and then more ITIC is another one. I think IEEE 1680 is a standard, IEEE 1680. They all give you grid standards. That means you have to essentially design this for 1.2, because usually it goes to 20% more. And also it goes to 0.9, but most of the charges are wide range anyway, so we should be able to meet with that. So this is, if you're doing a lot of lab tours, I'm assuming, in IAC, right? So as a part of that, you will find this converter. Professor Vishnu Iyer's lab, right? I saw this package, and so it has 3-port EV charger for 3 separate ones. He has a current source DC-DC converter with some ZVS, and then 3 separate sockets. I think they support 48, 60, and 72 volts. See, what he was telling me that in India there's not much of a standard. So when you go to a lab tour, maybe you can check that out today. And then you have a 3-phase grid-connected converter. I tried very hard to find Kaushik's scooter charger, but it wasn't there in the publication. Not yet, right? You're still secret. Okay. Okay. So 3-phase grid-connected EV chargers. You have so there are plenty of variations of single phase. So then the 3-phase. You would normally put it in a hotel, I think, in a IAC, in a building, at homes at least. In India, there is no 3-phase, right, at home. There is 3-phase? Oh wow, okay. My dad is a power engineer. I should have. I stayed most of the time in the power plants. I should know. But we had 3-phase. I thought that was because I was staying in a power system in the electric power, homes. So here we have 3-phase. So in most of the U.S. homes are single phase. It's actually dual phase, 120, 240. It's the same single phase, but 120 and 240. The cooking range, electric cooking range, is actually 240. The air conditioning is 240. The dryer, the cloth dryer is 240, and of course EV chargers are 240. Fridge, microwave, everything is 120 volts. So we are limited to 120 volts. We are limited to 1.5 kilowatt for 1.2 kilowatt, I think, because in the US we don't have fuses, we have circuit breakers. So the circuit breakers will trip at 13 amperes at home. So 13 amps times 120 is like less than 1500 watts. So these are 3-phase chargers. If there is at home, then you can actually have a little bit higher power charge for your car. So level 2 mostly is commercial EV stations. So there you have a typical block diagram of a DC charging station would be a PFC, which today is totem pole, right? And then you have a high frequency DC-DC converter. And there's a vehicle interface kind of a plug. If you go to Tesla, you have a separate plug. And then if I go to, in the US, there's something called Electrify America charging stations. there's an interesting background behind Electrify America charging stations, because this guy Volvo, I think he did cheat on gas emissions, right? So there was a graduate student, PhD student, who was doing this work in a university. I found out that whatever they were publishing was incorrect, because he was not able to replicate the results. And it became a huge story, and then they were fined so many billion dollars for ethically violating the emission standards. They were falsifying something, and they had put electronic circuitry to actually change something. So it's very, very deep-rooted within the company. Anyway, so like everything, whatever happens, whenever such things happen, they say impose the fine. As a part of the fine, electrify America. That means build all these stations for electrification. So now you will find a lot of those Electrify America stations all over in parallel with Tesla stations. And then, so most of them have their DC fast chargers, right? And then you can find them I think they're popular in Walmart. So if you go to Walmart, any Walmart, you should be able to find Electrify America. There's an app also, you can figure out where it is. So there you can connect it to the so if you bring in your Tesla, you cannot connect that. You have to purchase a plug to do that. And then, and Tesla doesn't want you to go there. So they'll sell the plug at $600 or some such silly plastic thing, right? So anyway, so there you have so there's so many approaches. So again, I found this on IAC, right? So you're going to the lab, so you should actually look out for these. Ask many questions, since I'm not covering all the approaches here. So it's like a three-phase, obviously voltage source, DC link, and then you have a DC-DC converter, and then you rectify. So as you can see, there are no diodes used, so this is entirely bidirectional. So later on, we'll see why these bidirectional charges are important. So majority of the EV chargers are not bidirectional today, so because they want to save on cost, so it's just one direction power. So to participate on grid services, you need bidirectional. So you can see that this one I found for Kaushik's paper. I don't know if he still has this in his lab or he dismantled it. It's not there anymore. Okay, they cannot see that. So this is an interesting concept where you have a three-phase, and then you have obviously you have a lot of switches. So this is 3 to 1 phase, right? So you take 60 hertz or 50 hertz and directly convert to high frequency, right? And then that high frequency is again comes back here, and then you do convert that back to DC, right? And then so there is no capacitors or energy storage. So this could be very compact kind of design, right? And then the entire any capacitor which appears the DC link capacitor will appear only on the other side, right? And because the three-phase system converts to single phase, and then this capacitor should not be that big. So like it still has to store twice the frequency. So this is I didn't see any commercial charger on that, but maybe there are. I think Japanese are fascinated with this converter. So I think Yaskawa has a motor drive which is 3-phase to 3-phase, adjustable speed motor drive commercially available. I think now discontinued. We work a lot with Toshiba in Houston. So they were saying, yeah, Yaskawa drive is not going to make money, right? So that's a 3-phase to 3-phase. This is only single phase. So if you add one more phase, you'll add, one more such 6 more switches. So you have, so that's a converter. Now let's look at integrated EV chargers. I think this is a topic. I'm not sure. I did not find. I don't know if there's any commercial. Maybe some of them automotive engineers could tell us. So this is basically the. Hammett talked about that. There's a Reynolds patent, and then Reynolds is not using it, right, according to you. It's not using it. Anyway, so the assignee is Reynolds. Its date is 2014. So for students, I think if you want patents, I think you should go to USPTO or Google Patents. Now it is free, and you can download it. I think you should learn how to read patents, And then also patents are written by attorneys, lawyers, who are also many times engineers, but they write in attorney language, right? So, but you should try to understand that that's an important function of a patent. So if you join a company, they want you to come up with patents. They don't want you to write any papers, right? They want you to file patents and things like that, because it's not that you're trying to use the patent, but patents, you continuously file patents and keep it. So if the other guy sues you, you just pull out some of your patents and say, hey, you're violating mine. And then, then you get some negotiations like that. So it happens all the time. So that's why they keep on patenting everything. So this particular one has this integrated EV charger concept. I think Professor Hammer touched on it. It's basically you have, inside the EV, you have a battery, you have a traction inverter already, and you have a BLDC or brushless DC motor, which already exists. And now you come to charging point, charging place, like a parking lot in your home. You still have a, like I said before, rectifier, AC, DC inverter, and then you need a high frequency transformer and things like that, right? So this particular concept doesn't have a isolation right now, right? There are some other approaches. So here at least he's assuming a 3-phase. You can also assume single phase here as well. So he's using the motor neutral. So he's using the motor neutral. And then these motor windings as inductors, right? And then this one is using like an interleaved boost converter, right? So you just close this switch, and then you store energy here, and then you turn off the switch, the energy goes back like that, right? So it's an interleaved boost. You can operate in many different modes, but it's just easy to understand. It's a 3-phase, three-stage interleaved boost converter. That's what it is. And you can, this is already there in the thing. So because these currents are going to be flowing mostly DC, in a 3-phase transformer, if you supply DC, then you should have you should only have leakage inductance there, okay? Because the zero sequence impedance of at least for a 3-phase transformer is nothing, so it's just leakage. So here, that's what happened. Hopefully there won't be any torque generated, and the vehicle starts to move. Right? So you should not. So you should make sure that the torque doesn't generate. Usually, it should not generate, right? So this is the one of the concept. The same Reynolds patent. I think they keep on patenting. As I said, they keep on patenting whether they use it or not. So there's another same patent. You can see here what he did from before he used this one, right? I'm not sure why they use this one, but I think that's probably to make the power factor unity, harmonics, reduce the harmonics. But this particular converter is outside, right? All of this vehicle, this is inside the vehicle. And then in this concept, he used a bidirectional version of it. So to do V2G, I think that's the intent. So when you read these patterns, I would like you to I would like you to go back to the last few pages and then read the claim language. That's very important as engineers. One needs to understand the claim language, right? So when you read the patent claim, the claim number 1 is independent claim. So that one is they claim this, right? And then claim number 2 will depend on claim 1, and claim number 3 will depend on claim 1. Like that, or 3 and so on. So those are all dependent claims based on one independent claim. And suddenly after 7 or 8 dependent claims, an 8th one will appear which doesn't refer to anything. Okay, so that's going to be an independent claim. So the attorney will try to insert as many independent claims as possible. Patent examiners try to reject them. But in the law, if you have to study some domain of the law, so in the law, what happens? Each independent claim is a separate invention. So you don't have to actually show the circuit, but if a competitor has another circuit, another way of doing power factor correction, and the English language matches that circuit, they can sue you, say that you are violating my independent claim. So whenever there are some lawsuits, they will assert only one independent claim because they cannot prove the second independent claim. Or sometimes they assert the third independent claim, not the first 2. So those are, as you become an engineer, or you do startup companies. Whenever you do startup companies, you have to do patenting. Don't write papers. Keep filing patents. And then you have to work with attorneys to figure out how many inventions you can get out of one patent, right? So that is that one. And there's a third patent, of course, assigned to university. I think IISc also patents, right? Yeah, so I think you should patent as you're doing some new technologies already. So University of Maryland has this patent. So here is again, he's not using the neutral of the motor, but so here he has a single phase or three-phase rectifier, right? And then he's connecting to the negative of the DC bus, right? And then that's a three-phase inverter, traction inverter, right? And then he's connecting the positive portion to one of the phase A's. So basically, he's not disrupting any of these connections. These connections are already there. And then I don't want to go into all the operation of all this, but I think University of Maryland, I think Ali Reza has written a paper, good paper about that. I think you can follow all the design equations in that paper. So that's that one. And then I think Valeo is working with Siemens maybe. I think Valeo, I couldn't find a US patent, probably there's a European patent. I didn't do much that deep searching. So here they actually use the same triple H bridge charger for using the motor inductance and so on, right? And then the grid EMI filter, I think maybe there's isolation here and things like that. So there is a paper here which you can get it from the conference proceedings later on. And then this is the Continental all-charge system. Again, a European commercially available Continental all-chargers. There's a lot of activity there. So there you use a three-phase bridge. Again, he's using this motor inductance. And then this is the standard one, which we already talked about, like a three-phase converter. And then he puts this additional component, right? This additional component is put in he has to open those two mechanical switches, right? Open those two mechanical switches, so whenever you're charging mode, it is going through this boost DC-DC converter with isolation and then charging the EV battery, right? So this system sits ideal. When you close this and close this, your propulsion mode, you're just running the EV, going around, taking care of your business. I don't know if any of this commercialized, but these are done by respectable, all these commercial entities, so that there is some interest. And then I couldn't find a source for this, a company source, but it's galvanically isolated. I think Professor Ahmed talked about some 6-phase machines, maybe this is one of them. So I don't know how this works. It's like an E machine winding, 6 phases, and they rearrange the windings so that you have isolation. I don't know. I'm not a motor person. I don't know, this could be, maybe some of the ISC students could study this, and then this could have a potential to produce some torque, I don't know, while charging. And then another work from India, right? So because every PhD in India needs some external evaluator. I don't know why. You should remove that system. Okay, so most of what Kaushik and what we know tell me is that the external evaluators don't reply. So, but they find me somehow, everybody. So I usually reply, and I try to do it in 1 month, 2 months, because I know how difficult it is to get PhD here. You work so much, and you finally have a non-responding advice. It's terrible. That's very bad, demotivating, right? So that doesn't mean that I'm looking for more. But anyway, this is from BHU. Last December I was there, so I actually physically witnessed this project. So maybe that's the reason, I don't know, they sent me this thesis, right? So these figures are not from his thesis. In thesis, there are a lot more figures. I don't want to use his thesis figures. But this is from his paper, which is publicly available, right? Vehicular electronics transactions. So this is a student. I was telling Kaushik, maybe you should hire him, or I don't know, in ISC or something. Anyway, so this is a traction inverter, and then a traction motor, right? And then he's trying to reconfigure these things into these boost and then in a DC-DC converter, right? He's trying to reconfigure that. So what he has done is doing this. So the one part of the traction inverter, H-bridge is using it as a single phase PFC, right? A totem pole or something like that, right? And then he gets DC link. Once you get the DC link, and then he has the other phase which is available, and then he will put extra elements here, just like the other guy put extra elements. He will put these extra elements, do some disconnection. I think he will disconnect the mechanically something, and he will pass this. This is going to be a DC to DC converter, which is charging the EV battery, right? So that's what he's doing. So converter elements are extra components. So these are the converter elements are extra components which are placed, but reconfiguration switches are needed to open and close, and mechanical switches. And then one needs to make sure the motor does not produce torque during charging, and it doesn't move. Sometimes you can lock the motor, lock the rotor. So anyway, so that's his integrated EV charger concept with all these mechanical switches and things like that. I don't want to bore you, but this is what he did. He did on I think it's like a forward converter, with so he's using these two switches as a DC-DC converter, and he'll disconnect that power portion, and then he'll come back to the EV mode with these things, right? 5 mechanical switches, relays, configure. So I think it's interesting. I think on the same lines, you have a 6-phase motor. So if you have a 6-phase motor, you have a 6-phase EV inverter. So then this transformer, star delta, this transformer is only one which is on the ground, right? Whenever you pull to a charging station, there's a dumb transformer there. So then that's connected, and then the inverter is used to charge the battery. I think these folks claim that it's a very fast charger. I don't know. We need to look into the motor ratings. I think Emil is in Italy. I think he does some work for Italian companies. So this is a good one. And then this is again in the U.S., right? I think Princeton University professor. He's got an integrated EV charger concept, which looks to me the most simplest. No mechanical. There's only one mechanical switch. Look, if you pay attention to this one, there is this. This is this battery EV inverter. Then there is a motor. That's a traction motor. But in between these two, he attached a output filter, LCL filter, right? He attached an LCL filter purposely. And then that's also, most of the people who work in power electronics know that when you connect something here, you're trying to take care of the common mode and things like that, right? So that he's claiming that he'll protect the bearings of the motor. So during the normal traction operation, when you're going from place A to place B, you're just running the motor, running the motor with this LCL filter, and that's the motor which spins and it keeps going. But this is actually placed additionally, right? And now when you want to charge something, you'll come here, connect to 3-phase outlet, and then use this relay contactors. So you close this, and then you open this, obviously, right? You close that, close this, so this input comes in, LCL filter, and then this becomes a EV charger, right? Of course, the electronics has to be different. So seems to be, to me, when I looked at it, it's very simple. It has one contactor. It has the benefit of using this one. Motor windings are not used. Instead, output filter is placed, right? And of course, this is high frequency. Then the output filter components are going to be smaller. But while they're still there doing the traction operation, they give you benefit of sinusoidal voltage and whatever. So it reduces the dV/dt and then the bearing currents and the common mode and things like that, right? So the inverter doubles as a rectifier. Of course, no isolation is provided, whether you need, I don't know, maybe you should not sit in the car, but I don't know. So those are so this is something, another one, single-phase EV charger or 3-phase EV charger. Once again, it's very similar to the other concept. Like in the US, I said there are 120, 240. So you can open that and then you can do these things. So there are a lot of advanced controls and then that's what's needed. So fast chargers are the one which you need when you go from place A to place B. You need all these fast chargers, and you can see how the Tesla places these fast chargers. And then it'll be, I wish I had I think there's an app on my phone which shows all the fast chargers. There are so many in the US. I think Europe is popular. China has hundreds of fast chargers from Tesla. I think Middle East has a few, and so on. I wanted to see if India comes into picture. So 1 hour stop, to get charged up. You still have to put in 11 extra hours. Maybe that's the time you stop for snack or dinner or something. So anyway, so level 3 charging stations. How long do I have? Sorry, what time? We start 11. Okay, 10 more minutes. Okay, that's good. Because I want to listen to Chrysler. So I'll go fast. So here you have the level 3 charging aspects of it, right? So here you have high frequency, and then there's always a low frequency transformer. Everybody's talking about integrated solid state transformer or solid state transformer. We know that the solid state transformers are much more compact and so on. So there are many solid state transformer concepts. So I think this is the problem with my student who put so many animations. I couldn't remove them before I thought they were not there. So anyway, so here you have a solid state transformer where you have AC to, again DC, and this single phase B and phase C. So this is what we are working on, integrated solid state transformer. We have AC and then directly to go to DC. So conceptually, what we have is this concept. Maybe I can skip this and then go to the next slides. But here, what we have is a single phase, 3-phase, line to line AB, and then BC, and then CA. So you have a converter here, a line side converter, which are series connected, and then the other side is connected in parallel. So inside this box, you have a AC/AC converter cell. You have 4 switches, a weak DC link, and then a high frequency converter, which is actually producing high frequency voltages. And then on the other side, you only have diode rectifiers. So using this concept, one can actually do some things like that. So you have an incoming AC voltage here, 3-phase AC. One phase is coming here. So after that, you switch this kind of converter to make this voltage at the output of the transformer look like this. And then you can adjust the duty cycle here to make it smaller, whichever way you want to. And then the output, it's like a delta or star connected, and then you have a 3-phase diode rectifier. And then we show that this will work like a regular converter. And let me skip this because this animation will take me a long time. So what you have here is so what you have. Oh, it still has animation. Sorry. Okay. Yeah. So what you have here is a converter which is using this type of converters, right? Which is basically taking the input and then chopping up into high frequencies. And the other side is simply rectification. So once you do that, the input currents are not very good. They're basically square wave. So what I essentially did is took a 3-phase diode rectifier and made it into high frequency isolation. That's all I did here. So then, so with that, I can directly convert to DC and so on. So here you have the final AC side structure, weak DC link, 0 voltage switching, things like that, right? We still have 5th and 7th harmonic, but we can see how we can get out of that. So the way we get out of the 5th and 7th, one approach is to, as this is the only slide, I shall skip the other ones. So we have a AC-AC converter. We just make it into a 12 pulse. I think students ask me, it's high frequency, how does it work as a 12 pulse? But it does work, and then you get good elimination, right? So if I were to skip more of that, and then I'll leave the slides with you, right? So we found a lot of other applications. Maybe I can quickly review for the solid state transformer, which we are working with different companies, is to actually see the medium voltage drive, which has a 60 hertz transformer. And if you look at a medium voltage drive today, it has a lot of 60 hertz transformers and then the motor drive, right? So we work with Toshiba to make this into a medium frequency, or they don't want a high frequency transformer. They want a transformer which is around 1 kilohertz or 600 hertz to reduce the size to 1/3. So there we have AC-AC converter, standard star and delta, and this side is the same, right? So again, a medium voltage drive, which is 60 hertz transformer, 11 kV coming in, and there's so many transformers here. And then there's single phase, 3-phase rectifier, single phase inverter. They're connected in series, like a multi-level, running a big 11 kV or 3.3 kV motor drive. So these are commercially available. And so working with Toshiba and say, how do we actually make this into lighter weight transformer, right, as a next concept? So our approach would be to make the link frequency like this. On the other side, you simply don't change anything. Just keep the same things, and then everything should work seamlessly. Only thing you need to do is change these diode rectifiers to high frequency rectifiers. That's all. And then so for a conventional wind generator, you have a low step-up transformer. So you want to make that smaller. Then once again, of course, I drew it in a reverse way. Wind, that's the wind generator existing hardware. And then here you put in your solid-state transformer, which does this kind of thing, and then you get that, right? So coming back to the EV domain, I don't know about US, but Europe is talking a lot about second life batteries. What happens if all the EVs are used and the battery becomes useless? Battery no longer performs according to the EV, but this battery still has life. So you take out the battery, because it's no longer going 100 miles, it's only going 50. Customer doesn't want it, he will just exchange it. So remove the battery, do some refurbishment, right? And then you repurpose it, reuse it, but it doesn't go back into the EV. It goes back into your box, which connects to the grid, right? So these are called second life batteries. So there's an Israeli company called Sparkion, which is working on a lot of second life batteries for EV chargers, right? Maybe this makes sense to India because yesterday the Delta person was telling us that he cannot really connect a EV charger in some locations. So there you install second life batteries to make them fast charging, right? So you can give additional energy and so on. So few slides on the V2X aspect of it. So that's a new ABB V2X charging station, 11 kilowatt, and then what it can do with a lot of, it complies to all this OCPP and so on. So I want you to, as students, I want you to go to openchargealliance.org. I think there's a lot of webinars. They recently had a big conference in New Delhi, Open Charge Alliance. I think you should attend that to get some practically oriented. So this Open Charge Alliance has webinars and so on. So what they do is V2X support. So you have these chargers installed, So now what can I do? So this would be the concept. There's a AC power, and then V2X charger. There's a car. I may be at my home, but I'll join the pool. I'll join the pool of 1,000 cars in Bangalore, all over the place. So the pool will tell me what to do, right? This is very similar to Bitcoin mining. You're a miner with let's say 10 computers at your garage, and you want to mine Bitcoin. You cannot win the Bitcoin. You cannot mine it. It's only 10. You join the pool, and then you mine it, and then you get reward based on the pool. So same thing. You join the pool. The pool will do grid services, provide a lot of grid services and so on. So that's what the V2X grid support, right? TSO, I think in Europe is called transmission system operator. So the transmission system operator, they hope they can get 20 gigawatts of V2G aggregated, and they'll play the market. A frequency regulation, demand side management, a lot of those things, right? So I think those are important things to work on. I think this another one slide on cybersecurity, because I work a lot on cybersecurity. So there's something called a broken wire, wireless disruption for EV chargers. It has been proven that you can actually disrupt EV charging through broken wire by simply injecting an additional EMI. Many of these chargers don't have shielded cables. So you can sit there. You can probably enter the garage, or you don't have to enter the garage. You turn on your disruptor, then all the charging network can get disrupted unless you make amends here, you make redesign and so on, right? So that's a good topic to work on. I think that's my questions. Thank you.